Bismillahirrahmanirrahim. Assalamu alaikum, dear students. So, uh, the topics that we will be discussing in today's lecture are centrifugal compressors and axial flow compressor. So, if you remember in the previous class, we discussed about rotodynamic machinery in general, and then we talked about uh, impulse turbine. Okay, and also we draw the velocity triangles from where we can reduce and we can extract the relevant relationships for the power output, and similarly the diagram efficiency, etc. So today obviously we will discuss generally what centrifugal compressor and axial flow compressors are, and how they work. Means we will discuss about their working principle, and then as I told you that we will draw the velocity triangles for centrifugal compressor and axial flow compressor, right? And you know these like after discussing these things, there are also some auxiliary topics like degree of reaction and pre-whirl, etc. So we will have to discuss about those things, right? So you see, uh, if you remember, we have a lot of discussion about the compressors. Okay, so you know very well that a compression process is basically to increase the pressure of a fluid in order to make it travel to another place. Okay, or you can use it for some other purposes. And you know that the compressor will then be a mechanical equipment that is used to increase the pressure of a compressible fluid. So we have different types of compressors over there, right? We have positive displacement compressors and rotodynamic type compressors or dynamic type compressor. So today we will discuss about those things, right? Okay, so what a centrifugal compressor is? Centrifugal compressor is basically it works on the principle of accelerating a gas to a high velocity and converting its kinetic energy into potential energy, right? By decelerating the gas means that the impeller rotates and it imparts or converts the kinetic energy to potential energy, right? So in other words, you can say that a centrifugal compressor basically consists of a rotor. In this case, we are saying impeller, to which a number of curved blade or vanes are attached, right? Let me have this pointer over here. I don't have that. Right. So these are basically these curved vanes. These are basically known as impeller blades, right? This is impeller. You can see this one, right? So the gas, what happens is this is I, right? This is this one. This is I, right? So the gas enters the eye of the impeller and it is accelerated to the outward edge of the impeller as it rotates. So the gas comes here and right, and it is impinged in this impeller, right? And then the impeller since rotates, so it imparts kinetic energy to the working fluid that is impinging over here, right? And then after that, these are basically the curved veins. These are the veins, they are stationary, right? So if you see here, it then enters a diffuser where its direction is changed, causing deceleration. So if you see here, the direction, like it should you know, the direction of the working fluid flow should be like this, but you see here that there is a vein over here, so the direction is changed. This direction change is obviously it decelerates the fluid. Okay, so accelerated by the impeller and decelerated by the vanes, okay, are decelerated by the stators, this diffuser section, right? And this deceleration converts the kinetic energy to potential energy, and that is basically in the form of pressure. And even if you look at this one, so you see here the area of this, if you look at the area, okay, this area, that is the exit area, right? And this one will be the inlet area. So the exit area is more than the inlet area. This means that the for subsonic flow the pressure will increase, right? This is actually diffuser. You know, just we have discussed about the nozzle, that is the voice, the reverse, okay, in operation, as far as diffuser is concerned. So if you look at this one, the area, instead of decreasing in case of nozzle, it is increasing. So the pressure will increase over here. So first it is accelerated by the impeller, then decelerated because the direction is changed, okay, and then after that it is, you know, you see this portion of the vane, it is configured like this, that it is having larger area at the exit, so the pressure is increased, right? And even if you look further to this volute casing, right, this casing, so this is also a type of diffuser. It further increases the pressure of the working fluid, and at the end you are having a high pressure working fluid over here. So the pressure of the working fluid at entry, let's say this is P1, so we are having the pressure P2 over here, right? तो यहाँ से जो है ना आपके पास ये प्रेशर इस तरह इंक्रीज करता है, right? So this is generally the working principle of the compressor. And if you remember, I told you earlier that in all types of these rotodynamic or turbo machines, we have a rotary part, right? That rotary part is impeller over here. In axial flow compressor, that will be a rotor. So the energy transfer takes place. If you remember, we discussed. Now, what is the energy transfer over here? The energy transfer is that the fluid is entering the impeller at low energy, right? And the impeller rotates. And who is rotating this impeller? Obviously, the input. This is you know, mounted on the input shaft, and we are working on this. The work is consumed, okay, or the power is consumed by this impeller, and that kinetic energy is converted to pressure energy, is you know, we discussed, okay. So acceleration and deceleration takes place, and that's why you know, the pressure is increased. And if you know, such a compressor which works on this principle, where the impeller increases the kinetic energy of the working fluid, and you know, then the curved vanes, they decelerate the working fluid, and when it exits the vanes with a larger area, the pressure is further increased, and at the end it is given to the volute casing, and the pressure is further increased over there also. So in this way, when the pressure of the working fluid is increased, this type of compressor is known as centrifugal compressor, right? So this is actually the working principle, a schematic and cutaway section, you know, the diagram, and this is the actual centrifugal compressor. And even if you look at this impeller of a centrifugal compressor over here, okay, so we have actually plateless impeller. Plateless impeller का मतलब ये है कि आपके पास जो है ना, just we are having, you know, one plate, you know, these are actually the blades, right? These are the blades, okay. And if these blades are mounted on a single plate, so this is single plate impeller. And if you have another plate over here, okay, on the top of these blades. So we have two blades impeller. No, different configuration are there. Okay, and you can also see the direction of flow of or direction of rotation of the impeller, as well as the direction of flow or motion of the working fluid. Right now, discussing further about the centrifugal compressor, the mechanical energy is provided to the rotor from some external source, as we discussed, because the compressors are power consuming devices. So as the rotor rotates, it sucks the air through I. Okay, these are the things I discussed verbally, and these are the black and whites are writing over here. Increases its pressure due to centrifugal force, and forces the air to flow over the diffuser. Finally, the air at high pressure or higher pressure is delivered to the receiver. And you can see that in fact here the air enters the impeller radially and leaves the vanes axially. Okay, this is important, right? As I told you that to draw the velocity diagram, okay, for different types of rotodynamic machines, the basic principle remains the same. Okay, we will be having, you know, absolute velocities, relative velocities, blade velocities, the same angles. Okay, you know, alpha 1, alpha 2, right, and beta 1, beta 2, etc. So the most of the things are the same, but here if you see, like over there the nozzle was inclined in the impulse turbine, the nozzle was inclined at certain angle. Okay, so that was actually the angle of incidence over there, alpha 1. Now here, or alpha I, you can say inlet angle. Now here what they are saying, that air enters the impeller radially, right? तो अब इस radial के क्या मतलब है? Radially actually means this thing, right? That this is the eye and this is the impeller. So this is a radial entry. Okay, so you will see that in the velocity diagram, that what actually we mean by this radial entry. Okay, and leaves the vanes axially. The curved vanes as well as the diffuser are so designed that the air enters and leaves their tips tangentially without shock. Okay, and they are saying that, okay, we will also talk about this shock wave production also, okay, at some point, because if this is actually exactly the radial entry, okay, so we are having only the flow velocity, there will be no tangential velocity or whirl velocity. Okay, velocity of whirl. So this, you know, high flow velocity actually makes it, you know, produces a shock wave. Now how to you know, avoid that shock wave, we will discuss that. We are actually having a pre whirl over there. Okay, we produce a pre-whirl. Moreover, their surface is also made very smooth in order to minimize the friction losses. Obviously, the surfaces of the impeller or the blades, they are made, you know, very smooth for you know, each and every blade. If you look at even the compressors of the, you know, the blades of the axial flow compressor, you will see that they are very fine. Okay, and they are very smooth. The surface finish is very fine. The work done by the centrifugal compressor or the power required to drive it can be found by velocity triangle. So how much power is consumed or how much work per unit time is consumed by the compressor, that can be found out with the help of, you know, velocity triangle. So if you look at, before discussing this, okay, I actually took these slides from some document I will share with you, you know, over Google Classroom. Okay, so if you see here the velocity triangles for moving blades of a centrifugal compressor, so they are saying that consider a stream of air entering the curved blade at C. Where is C? C is basically this point. Okay, this is point C, and leave it at D as shown in this particular figure. Okay, and then they leave it at D. You see here, this is basically a, from here to here, this is a single blade of the impeller. Okay, this is actually a single blade of the impeller, like this one. This is actually taken as, and this is, you know, separated from this centrifugal compressor and this impeller, and it is actually shown over here. So this is actually the same blade. So the air enters the working fluid enters at C, okay, here, and this one is it leaves at D, right? And then they are saying that now we have to have some nomenclature. So now let us draw the velocity triangle at the inlet and outlet tips of the blades as this is shown over here. Okay, obviously we need to draw the velocity triangle inlet and exit. So inlet is basically to this inner tip. Okay, this one, this is the blade, the whole blade. So this is actually the inner tip and this is the outer tip, right? So we need to draw the velocity triangle inner tip we are drawing it. So this will be the inlet velocity triangle, and at the outlet tip when we are drawing it, so this will be the outlet velocity triangle, right? And we are having some nomenclature. What is that? A bit different from the one that we discussed for the impulse turbine. So VB, linear velocity of the moving blade at inlet, right? So blade velocity, this is the absolute velocity of the air entering the blade, right? And this is the relative velocity of the air, to the moving blade at inlet, right? This is a relative velocity. And they are saying that it is the vectorial difference between VB and V, as we discussed, right? This is what? This is the vectorial difference of VB and V, the blade velocity and the absolute velocity. इसका जो vectorial difference होता है, that is your relative velocity, right? And then we have VF, that is velocity of flow at inlet, and theta, angle which the relative velocity makes with the direction of motion of the blade. Previously this was alpha, right? So this is for inlet, okay? And for the outlet velocity triangle, just we need to have the subscript 1. So VB1 will be the linear velocity of the moving blade at outlet, and this V1 will be the absolute velocity of the air entering the blade at outlet. And same is the case for VR1, VF1, and for in place of theta we are having phi. Okay, so it may be seen from the above that the original notation VB, V, VR, VF stand for the inlet triangles. Notation zaruri hai cha, isko samajhna, because these are used in the diagram, so you need to know that the notation with suffix means 1 they are used for, or they are stand for the outlet velocity triangle, right? So now if you understand till this point, okay, the nomenclature, that what VB, V, VR, VF, and theta, etc., they are different notations for the inlet and outlet velocity triangle. Then we can look at the velocity triangle also, right? So as I told you that this is the impeller, okay, this is the impeller part, and these are actually the vanes. So obviously the vanes are stationary and the blades are the impeller rotates, okay? So we need to separate this impeller over here, a blade of impeller, ठीक है? ये एक blade of impeller है. Now जिस तरह हमने देखा, as we saw over here, that air enters the impeller radially. By this radial entry actually we mean that if you see here, this is the I, this is radius, ठीक है? Radial, इसको radial कहते हैं ना, this is radial, ठीक है? So this is radial entry. This is what? This is radial entry, right? So if you see here, now you need to look, this is actually the main difference between the previous ones that we discussed, like the velocity diagrams, and this one. The rest of the things will be the same mostly. So this is actually the radial entry. Now this radial entry is what? This is a, this one is this radial entry from here, this one, this is radial entry. Okay, so you say that this is the absolute velocity, right? And the blade rotates in this direction, okay? This is the blade rotation direction, this one. ये blade इस तरह rotate करता है, right? The blade is rotating like this. The blade is rotating like this, okay? So this is the blade velocity, and this one is the absolute velocity, right? And if you see here, they are making an angle of what? An angle of 90 degrees, right? So actually having this 90-degree angle, okay, we will be having zero variable velocity, right? Previously आपके पास क्या था? And obviously the vectorial difference of VB and this V, the absolute velocity. This is the relative velocity at entry. So let us, and the angle made by relative velocity with this blade, that is known, that is denoted by theta. Okay, so this triangle ABC, this triangle is the inlet velocity triangle. All right, so if you see here the velocity triangles for a centrifugal compressor, if you look at this one, so this, there is no, because you see here that, let's say for example, if you have the absolute velocity, okay, and there is some angle, so you can have two components of it, right? Let's say for example, if you are having this velocity, let's say, is directed like this, so obviously we'll be having two components. One will be a radial component and the other one will be tangential component, right? So this is not the case over here. So for that reason, this, the whole of this velocity will be then velocity of flow. There will be no tangential component, because if you look at the cos 90, cos 90 is what? Cos 90 is 0, right? Because the horizontal component, okay, that is with cos, and here the cos is 90 degrees. So cos 90 is 0 के बराबर होता है. So for that reason, we don't have the viral velocity, or velocity of viral, or tangential component of velocity. So whole of the velocity of the working fluid is velocity of flow. Okay, that is यहाँ पे जिस तरह लिखा है कि v is equal to vf, that is velocity of flow. There is no tangential velocity over here, right? So बल्कि चलिए यहाँ पे ही हम थोड़ा सा डिस्कस कर लें. So for that reason, because of this huge velocity, and that is flow velocity, okay, if you remember over there, we have actually a very small amount of this flow velocity, okay, but here this velocity is too much. The whole of the absolute velocity is the flow velocity. So for that reason, it actually is impinging with a high velocity here, and it produces a shock wave over here. Okay, so इसलिए जो है ना यहाँ पे shock wave produce होता है. So to avoid this shock wave, what happens is that this radial entry is a bit diverted. ठीक है, इसको radial नहीं, ये जो angle है ना 90, इसको हम थोड़ा सा चेंज करते हैं. ठीक है, द एंट्री ऑफ द वर्किंग फ्लूइड थ्रू आई इज नॉट exactly radial or having 90 degree angle with the blade velocity, but it is actually diverted and having some other angle other than some angle that is other than 90 degree. And this way, obviously, if you are having this type of entry, or if you are decreasing this angle, so obviously we'll be having two components. One will be the flow component, and other one will be the tangential component. And that tangential component of the velocity is causing whirl in this blade, and that is basically known as a pre-whirl. तो pre-whirl का एक फिनोमेना यहाँ पे होता है. अच्छा, ये डायरेक्शन कैसे हम चेंज करते हैं? डायरेक्शन इज चेंज यूजिंग गाइड वेन्स. यहाँ पे गाइड वेन्स होती हैं. ठीक है, जिस तरह मैंने आपको बताया था कि एक्सियल फ्लो कंप्रेसर्स एंड एक्सियल फ्लो कंप्रेसर्स वी आर आल्सो हैविंग, वहाँ पे आप देख लेंगे, वी आर आल्सो हैविंग गाइड वेन्स that changes the direction of the working fluid at the entry. ठीक है, तो उसकी जो एंगल आप रखना चाहते हैं, तो वो एंगल जो है ना आप रख सकते हैं. गाइड वेन्स आर फिक्स्ड. ठीक है, दे आर आल्सो नोन एज विकेट गेट्स. दे आर फिक्स्ड. जो हमारे पास जो टर्बाइंस होती हैं ना, that is in hydraulic turbines, so there are wicket gates. Those wicket gates are nothing but the guide vanes. They actually and they are fixed. You can change the direction, but you need to stop the process, and then you can change it, just like changing the pitch of the propeller in propeller type aircraft. So you can have then pre-whirl, यानी हम खुद जो है ना इसमें whirl जो है वो प्रोड्यूस करते हैं. Anyway, so then after that we have this exit velocity triangle. So you see here, this is the blade velocity. Okay, blade velocity जो है ना, the blade is moving in this direction, right? So this is actually the blade is moving in this direction. So this is this one is the blade velocity, and then v1 is the absolute velocity in this direction, right? Because the absolute velocity direction remains the same. Okay, ये जो है ना इसकी डायरेक्शन सेम होगी, रिलेटिव की जो है ना वो पूरा डिफरेंट हो जाती है, राइट? दिस इज एक्चुअली द रिलेटिव वेलोसिटी डायरेक्शन। जिस तरह ये मैं बताया था कि एंट्री to the impeller is radial and its exit is axial, ठीक है? So this is actually the axial exit, right? So this is v1, the absolute velocity at exit, and this one is this is vb, this one f e ref, this is vb1, and the angle between these two is denoted by beta, and the angle between vr1 and vb1 is denoted by phi. And if now here we are having what? We are having an angle between VB and V1, VB1 and V1. There is an angle beta that is what? That is less than 90 degree. तो यहाँ पे आपके पास फिर component होंगे, right? So V1 is then resolved into two components. One is VW1, that is the causing whirl, and the other one is VF1, this one, this vertical one. This is the velocity of flow, right? So if you look at these two velocity triangles and make a combined velocity triangle, okay, or even from these two you can so even a smaller one is also given over here. This is the outward velocity triangle and this one is the inlet velocity triangle. Now from these two triangles if you look, so यहाँ से जो है ना आपके पास you can find out that how much power is consumed by the compressor. Okay, so the air enters the blades along AC. This is the explanation. Okay, ये आप खुद फिर देख सकते हैं. The air enters the blades along AC with a velocity v. Since the air enters the blade at right angle, ये हमने discuss किया, right radially to the direction of motion of the blade. Therefore, velocity of flow is there will be equal to the air velocity. The air velocity is basically the velocity of flow. Okay, moreover, velocity of whirl at inlet will be 0 because of that 90-degree angle, right? The linear velocity or mean velocity of the blade VB is represented by BA in this particular diagram. This is BA. BA is your blade velocity, and the length BC represents the relative velocity, right? The vectorial difference of VB and this V is your VR, right? And they are then saying that the air now glides over and leaves the blade with a relative velocity VR1, which is represented by DE. This one, this is your relative velocity VR1. Okay, so the absolute velocity of air V1 is it leaves the blade is represented by DF inclined at an angle of beta with the direction of the blade motion, right? So this is your V1 and it is inclined at beta with the direction of motion of the blade. And then they are having two components. The tangential component of V1 represented by FG is known as VW1. Okay, ये FG जो है ना, this one FG, this is your VW1. And the axial component of V1 represented by DG is known as R. This is the velocity of flow over here. Okay, so if you know this M is mass of air compressed by the compressor in kg per second, so using Newton's law you see that force applied on the blade will be what? Mass of air flowing M into change of velocity, right? It's the same thing, right? So वही फार्मूला है m dot into v2 minus v1 rc2 minus c1. So m and this is the velocity difference, they are in the opposite direction. So इसलिए जो है ना इसको यहाँ पे minus जो है वो plus हो जाता है, right? And since you know very well that this is basically vw, that is velocity of whirl at inlet, which is what? Which is 0 over here because the entry to the centrifugal compressor is radial. So ये VW जो है ना वो 0 जाता है, तो इसका मतलब ये कि जो force apply होगा on the blade that will be m into VW1, where m is the mass in kg per second and it should be m dot, and VW1 is the velocity of whirl at outlet. Okay, now the power is very simple. You just need to multiply this force with what? With the velocity of or the blade velocity. Okay, VB1. तो यहाँ से जो है ना आपके पास क्या आ जाएगा? This is the power consumed by the compressor. Okay, or the power required to drive the compressor. Right. And further explanation is a little bit about how to find out this VB and this VB1. So you see here they are the linear velocities. Okay. तो VB क्या है बेसिकली? VB is the linear velocity at the inlet tip, right? And VB1 is the linear velocity at the outlet tip, यहाँ पे, right? The linear velocity VB यहाँ से, और ये जो है ना आपके पास this is outlet tip. ये this is we have actually this जिसको हम कहते हैं root, right? And this one is the outer tip. सो रूट के ऊपर आपके पास जो वेलोसिटी है और टिप इसको हम फाइंड आउट कर सकते हैं बिकॉज दिस वी बी इज पाई डी एन ओवर 60 वेयर डी इज द इनर डायमीटर. यहाँ पे शायद कहीं लिखा होगा इंटरनल डायमीटर एंड डी वन इज द वी बी वन इज पाई डी वन इन ओवर 60. ठीक है, ये जो है ना आपके पास एक्सटर्नल डायमीटर है. तो इंटरनल डायमीटर एंड एक्सटर्नल डायमीटर यहाँ से आप देखेंगे. ओके, दिस इज इफ यू आर हैविंग the radius from this point. Okay, so this will be your D and this will be your D1, right? And other things are constant, or you can find out the value of n from the tachometer. यहाँ से जो है ना आप n को जो है वो find out कर सकते हैं. So all the things are known, so you can find out what the blade velocity at outlet will be, and obviously it will be greater than VB. And the reason is very obvious, right? Because this D is increased from D to D1. बाकी दो चीजें तो सेम हैं, but this D is increased. So for that reason, this blade velocity will be over here. This is increased, and this is more than VB1, right? They are then saying that okay, where D and D1 are the internal and external diameters of the ampere, and under ideal conditions, are in other words for maximum work के लिए आपके पास क्या होना चाहिए कि the velocity of whirl at outlet, it should be equal to velocity of blade velocity at outlet. Okay, तो ये means that actually this is causing totally whirl in the blade. Okay, जो आपके पास blade की velocity है ना, it is completely converted to increase the velocity of the working fluid, right? So for that reason they are saying that the ideal work will be equal to m VW1 whole square, or in place of VW1 you can also write VB1, that is the blade velocity at exit. So if you want to find out the maximum work, okay, the condition where we will be having maximum work, okay, then you can use this simple relationship, right? Okay, if you understand till this point, so this was actually about the velocity triangles, about the axial flow compressor. Okay, so you see most of the things are the same, but there is actually a condition where the entry of the working fluid is at this radially, so there is no whirl velocity over here at first, right? Okay, there is a simple example. You can just do it, right? And a centrifugal compressor running at 2000 rpm receives air at 17 degrees C. So your T1 is given, you can convert it to Kelvin, right? If the outer diameter of the blade is 750 millimeter, so 0.75 meter is the outer diameter. D1, find the temperature of air leaving the compressor. You need to find out what? We need to find out T2, that is the temperature of the air leaving the compressor. Take Cp is equal to 1 kilojoule per kilogram Kelvin, right? So we have this simple formula that the blade velocity at outlet is equal to pi d1 n over 60. So from here you can find out VB1, right? And you know very well that work done is equal to what? is equal to maximum work done is equal to MVB1. So we have mass, and similarly you can find out 6.178 kilojoule per second. And we also know that this is actually the maximum work, right? And you know that work is also MCP delta T, right? So in terms of enthalpies, so this is W is equal to MCP delta T. So work, we have found out the value of that, and then MCP T2 minus T1, all the things except T2 are given. So you can find out the value of T2. That comes out to be 23.178 degree centigrade, right? So इसका मतलब यह है कि during this compression process, although we don't want the air to be, you know, heated, the working fluid temperature should be increased, but it is increased a little bit, about 5 to 6 degrees, and it is like this, right? And there is another example. Okay, I think you can also do this. This is actually particularly you need to draw the diagram over there, but they are saying that a rotary air compressor, a rotary compressor से यहाँ मुराद centrifugal compressor है, working between 1 bar and 2.5 bar, has an internal and external diameter of impeller D1 and D2. They are D and D1 are given to you. The vane angle at inlet and outlet are 30 and 45 degrees, right? So these are actually the vane angle at inlet and outlet. If the air enters the impeller at the vane stationary होती है at 15 meter per second, enter the impeller, the air enters the impeller, ये basically आपके पास absolute velocity at entry है जो कि flow velocity होती है. Find speed of the impeller in RPM 1 and work done by the compressor or work consumed by the compressor per kg of air. Okay, so P1 is given to you, P2 is also given to you, D1 are given to you, and theta and phi are given to you, right? And absolute velocity is also given to you. You need to find out these two things, right? तो इन जो है ना आपके पास क्या है, स्पीड ऑफ द इम्पेलर इन आरपीएम है. तो ये रेफर करता है किस चीज को, ट्रायंगल 29.6 को, ठीक है. तो यहाँ पे आप अगर देख लें, दिस इज एक्चुअली दैट फिगर. सो फ्रॉम दिस वन यू विल सी दैट जो हमारे पास वी बी है, बल्कि आप टेंजेंट 30 अगर आप देख लेना, बहरहाल इसमें एक्सप्लेनेशन की ज़्यादा ज़रूरत नहीं है, यू नो वेरी वेल दिस थिंग, ठीक है. टेंजेंट 30, दिस फ्रॉम हियर, दिस इनलेट वन, टेंजेंट 30, दैट इज योर वी बाय वी बी, दैट इज इक्वल टू वी बाय वी बी इज टेंजेंट 30. तो इफ़ यू आर इंटरेस्टेड इन टू फाइंड आउट वी बी, तो वो ये जो है ना आप क्रॉस मल्टीप्लाई करके यू कैन जस्ट लुक एट दिस वन, ठीक है. तो यू कैन फाइंड आउट द वैल्यू ऑफ वी बी, दैट इज द ब्लेड वेलोसिटी एट इनलेट, राइट. एंड you know very well that blade velocity VB is equal to pi dn over 60. तो यहाँ पे ये जो आरपीएम जो है ना इसका, सॉरी आरपीएम सेम होगा, आरपीएम जो है ना आप फाइंड आउट कर सकते हैं, राइट. Then work done by the compressor per kg of air. Okay, so from the same triangle, you know, we need to find out what? We need to find out VB1. ठीक है, तो ये आपके पास ये है VB1 डिवाइड बाय VB इज इक्वल टू क्या होगा, मैं डायरेक्टली आपको बताता हूँ, पाई D1 ओवर 60, राइट. एंड डाउन देयर वी विल बी हैविंग पाई DN ओवर 60, ठीक है. तो एन पाई पाई ये सारे कैंसिल आउट हो जाएंगे, 60 कैंसिल आउट हो जाएगा, आपके पास जस्ट D1 बाई D2 रह जाएगा, D1 बाई D, and if you cross multiply this, so you can find out the value of VB1. VB is known to you, D1 and D are known to you. You can find out that VB1 will be equal to 51.96 meter per second, right. And velocity of whirl at outlet from the same diagram, ठीक है, क्योंकि यहाँ पे लिखा है कि ये जो हमारे पास velocity of flow at outlet है, and this is equal to velocity of flow at inlet, and this is the absolute velocity which is given to you, that is 15 meter per second, right. So VW1 आप जो है ना फाइंड आउट कर सकते हैं इसी डायग्राम से. Where is that VW1? तो यहाँ से जो है ना आप फाइंड आउट कैसे फाइंड आउट करेंगे, VB1, ठीक है, VB1, ठीक है, माइनस यहाँ से जो है यू कैन फाइंड आउट दिस वैल्यू, ठीक है, या इफ यू सी हियर, so you can find out the value from here also, just playing with that triangle है, ठीक है. You can find out the value of that comes out to be 36.9 मीटर पर सेकंड, ठीक है. और अगर आपने मैक्सिमम पावर जो है वो work done by the compressor or work consumed by the compressor. अपने work done should not be there, it should be work done by the compressor on air आप कह सकते हैं. That will be m, right? This is actually the kg of air per kg of air. तो ये this is actually the relevant formula. ठीक है, is a force and this one is the velocity. That is basically this should be w dot. ठीक है, जिसको हम पावर कहते हैं. That comes out to be in joule per second 1920.44. ये आपके पास ये आंसर आ जाएगा, right? Okay, so this was all about compressor, centrifugal compressor. ठीक है. Now the next topic is about the axial flow compressor. ठीक है, तो ये थोड़ा बहुत हमने डिस्कस किया भी है when we were discussing about the gas turbine power plant, but let us look at this thing in detail, what this axial flow compressor is. So you see here that axial flow compressor is in its simplest form consists of a number of rotating blade rows fixed to a rotating drum. ये जो है ना आपके पास क्या है, this is a rotating drum. ठीक है, this is a rotating drum into which curved blades, okay, are rotating blades. These are the blades, they are mounted on, you remember this is a cutaway section. ठीक है, तो ये जो है ना आपके पास क्या है, blades हैं, they are mounted on this drum, right? And the drum rotates inside an airtight casing to which a fixed stator blade rows is shown in this particular figure. They are attached, right? As I told you that basically this is a drum upon which blades are mounted, and the combination of the drum and blade, this is basically known as rotor or rotary part of the air compressor. Okay, since we discussed earlier that there could be, you know, there should be some, you know, runner or impeller or rotor. So this is actually that rotor, okay, which imparts kinetic energy to the working fluid. One. Then the blades are made of aerofoil cross section to reduce the loss caused by the turbulence and boundary separation. Obviously, these are actually to avoid losses. They are actually made of aerofoil cross section, okay, and very smooth aerofoil cross section. Okay, in order to avoid friction, right? So this is the rotor, blades mounted on this drum. This constitutes this rotor, and this is encapsulated, and this is inside this airtight casing. Okay, but as I told you that the casing is not a simple casing. Okay, on the periphery of the casing we have rows of fixed blades. Okay, these are known as vanes. It's called fixed blades. तो जो ड्रम के ऊपर माउंटेड है इसको हम ब्लेड्स कहते हैं, एंड केसिंग के ऊपर जो माउंटेड है उसको हम कहते हैं rotor and stator, right? So these are this is rotor, and when you put this rotor inside this airtight casing, you know, this actually makes these as a stators. Okay, and you know, this row of blades and a row of stator, this is known as one stage of a compressor. ठीक है, सो अगर इस चीज को आप देख लें तो दिस इज वन स्टेज ऑफ अ कंप्रेसर, 2 3 4 5 6 7. सो दिस इज एक्चुअली जिस तरह आपने वहां पे देखा था. ठीक है, मैंने आपको बताया था कि वी विल डिस्कस अबाउट दिस थिंग लेटर ऑन. सो दिस इज 7 स्टेज एक्सियल फ्लो कंप्रेसर. ठीक है, तो यहाँ पे जो है ना, दिस इज योर केसिंग, दिस इज यू नो द एयर एंटर्स हियर, ओके, एंड इट एग्जिट्स फ्रॉम हियर, and the fluid is accelerated initially, right, and then decelerated using these fixed blades. Okay, and this acceleration and deceleration basically causes the pressure to increase. ठीक है, ये प्रेशर. दूसरी बात ये भी है कि इवन इफ यू लुक एट द, ये तो कट अवे सेक्शन है, इवन इफ यू लुक एट द कॉन्फ़िगरेशन ऑफ यू नो दीज फिक्स्ड ब्लेड्स, तो ये जो है ना आपके पास एक डाइवर्जेंस सेक्शन बनाते हैं, मींस अ टाइप ऑफ डिफ्यूजर. ओके, सो यू विल सी दैट even if you look to the isometric view of the axial flow turbine. Okay, so the blades will be converging in shape, right? They will be converging in shape का मतलब ये है कि they are increasing the velocity, and as a result the pressure is decreased. But in case of compressor, they are the vice versa. The two blades, okay, they will be or you can say that their cross section will be like such, like um, the area will be increasing when the air travels from left to rightward. So the area increase का मतलब ये है कि आपके पास जो है वो एयर जो प्रेशर है वो इंक्रीज होगा, एंड इट विल लुक लाइक अ डिफ्यूजर. सो एक्सियल फ्लो कंप्रेसर का स्कीमेटिक डायग्राम है, एंड दिस इज द एक्चुअल डायग्राम. दिस इज द रोटर. ओके, दिस इज rows of blades जिसका अगर आप कट कर लेना, so you will just see a single blade up there and down there. This is the cutaway section, and this is the rotor. Okay, so this is a row of blades. Okay, and if you see here, so there is a space between these two rows. Okay, that space is basically filled by these when you fix this rotor inside the casing. So ये जो आपके पास स्पेस है ना, this space is occupied by the fixed blades. ठीक है, तो इसलिए जो है ना आपके पास blade and stator. ठीक है, एंड सिमिलरली यहाँ पे आपके पास ब्लेड्स एंड वेन्स. तो ये जो है ना आपके पास डिफरेंट कॉन्फ़िगरेशन के डिफरेंट स्टेजेस के कंप्रेसर बनेगी. ठीक है, सो दे आर सेइंग दैट द मैकेनिकल एनर्जी इज प्रोवाइडेड टू द रोटेटिंग शाफ्ट ऑब्वियसली, एंड फ्रॉम हियर, like in case of the gas turbine, we said that the high pressure turbine is dedicated, or the power produced by the high pressure turbine is purely utilized by the compressor. So actually this is that power. Okay, that the shaft is rotating. Which shaft? This shaft. Okay, and the power is given to this shaft by the high pressure turbine. Okay, which rotates the drum. The air enters from the left side of the compressor from here, right? And as the drum rotates, the air flows through the alternately arranged stator and rotor. So stator, rotor. Okay. So rotor accelerates this and stator decelerates this. Okay. And even further, the arrangement is like this, that they leave this blades and stators in a divergent section. So the pressure is increased over there. As the air flows from one set of stator and rotor to another, it gets compressed. ठीक है, वन सेट ऑफ स्टेटर से दूसरे स्टेटर एंड रोटर से दूसरे में जाता है ना, तो उसकी कॉन्फ़िगरेशन ऐसी है कि वो डाइवर्जिंग सेक्शन है, और इसलिए जो है ना ये कंप्रेस होता है. द सक्सेसिव कंप्रेशन ऑफ द एयर in all the sets of stator and rotor, the air is delivered at high pressure at the outlet. Okay, so the more are the number of stages, the more is the air compressed. ठीक है, तो अगर आपने ज़्यादा कंप्रेस करना है, तो ये स्टेजेस जो है ना हमारे पास ज़्यादा होती हैं. ठीक है, दिस इज कंट्रोल्ड. ये स्टेजेस अगर ना हो ना, यू रिमेंबर, राइट? फॉर एग्जांपल, इफ आई रिमूव दिस रोटर एंड दिस these stators, ठीक है, if I remove the rotor and stator, and let's say for example the air enters from this side, so this is divergent section. Based on the length and the inlet and outlet area, the air will be compressed, the pressure will increase for subsonic flow, right? But it is not controlled. Now here, if you want to compress it more, you need to impart or have the kinetic energy that is converted to pressure energy. तो आपने फिर इसकी स्टेजिंग करनी होगी. ठीक है ना, the more, later on we will discuss degree of reaction. The more the air is in contact with the rotor, the more will be the kinetic energy converted to the fluid. Okay, and in this way you can have more pressure from the axial flow compressor, right? This is the inlet and outlet velocity triangles. थोड़ा सा ये है मेरे ख्याल में, this is actually the, ये आपके पास एक्सिस है. अच्छा, ये दिस वन, दिस इज ये एक्सिस ऑफ, ये यहाँ पे आपके पास है, राइट? थोड़ा सा इसने सेपरेट वेलोसिटी डायग्राम है और कंबाइंड वेलोसिटी डायग्राम है, इसको थोड़ा सा आप देख लें. एयर जो है ना यहाँ से ऐसे एंटर होता है. ठीक है, द एयर एंटर्स फ्रॉम हेयर, जिस तरह आपने ये देखा, द एयर एंटर्स फ्रॉम हेयर. अच्छा, इसमें थोड़ा सा आप देखेंगे कि भाई एयर तो यहाँ से इसको मैं रब करता हूँ। अच्छा, बिकॉज right. So if you look at the inlet and outlet, these are the blades, right? uh, yeah, this is the rotor is rotating, जिस तरह मैंने आपको बताया, the rotor will be rotating in this direction. Okay, rotors are rotating like this, इस तरह rotate करते हैं, ठीक है. So this is actually the blade direction of rotation, ठीक है. ये VB जिस तरह लिखा है. So this will be the, you know, the rotor blade, and this is the stator blade. But you know, we are concerned with what? We are concerned with the rotor blade because energy transfer takes place over here, ठीक है. तो you can see here, यहाँ पे जो आपके पास absolute velocity है ना, absolute velocity is here. This is inlet. Remember, inlet is from up there, ठीक है. This is absolute velocity, and the angle made by the absolute velocity with the direction, the axial direction, okay, or the axis of rotation of the drum is denoted by alpha, right? And you know, this is the blade velocity, ठीक है. ये जो VB दिखाए गए हैं from here to here, this is the VB, blade velocity. And the vectorial, you know, difference between V and VW, this is known as VR, and the angle made by this VR with the axis of rotation of or the axis of the compressor, इसको हम कहते हैं बीटा. अब आप ये क्वेश्चन राइज, ओके, देन वी आर हैविंग टू कंपोनेंट्स, V velocity of whirl, and here इसका जो दूसरा कंपोनेंट होगा that will be velocity of flow. Now you can say that here we are having the flow direction is like this, but the absolute velocity direction is like this. So it is because of what? Because of having guide vanes over here. तो यहाँ पे जो है ना, ये डायरेक्ट एंट्री नहीं होती, यहाँ पे ये गाइड वेन्स होती हैं हमारे पास, ठीक है, guide vanes. And these guide vanes, based on their tilt or their angle of incidence, it can change the velocity डायरेक्शन, ठीक है. तो एब्सोल्यूट वेलोसिटी की डायरेक्शन जो है ना, इसलिए जो है चेंज होती है फ्रॉम दिस स्ट्रेटर वन टू दिस वन, ठीक है. सिमिलरली द आउटर वेलोसिटी ट्रायंगल को भी अगर आप देख लें, सो दिस इज, यू नो, दिस विल बी द this is the absolute velocity at exit, this is at inlet. So V1 and the same VB over here in this direction, right? And their vectorial difference is VR1, and the angle made by V1 with the axis is alpha 1, and the angle made by VR1 with the axis is your beta 1, ठीक है. So this is the outlet velocity triangle and this is the inlet velocity triangle. This is a single blade, ठीक है, ये सिंगल ब्लेड है आपके पास. तो सिंगल ब्लेड विद के ऊपर इनलेट, एंड दिस इज आउटलेट वेलोसिटी ट्रायंगल. This was the, these were the separate velocity diagrams, and if you combine them exactly in this manner, because VB is the common over here, ठीक है, ये VB है आपके पास. तो यहाँ पे जो है ना आपके पास क्या होगा, you can just combine them, superimpose inlet and outlet triangle on each other, and you will get this combined velocity diagram, ठीक है. इसको जो है ना आपने इस तरीके से ड्रा करना होगा, राइट. वेयर यू नो व्हाट इज, यू नो, B1, व्हाट इज बीटा 1, अल्फा 1, बीटा एंड अल्फा. द एंगल मेड बाय द एब्सोल्यूट वेलोसिटीज with axis is denoted by alpha and alpha 1. The angle made by the relative velocity with axis of the compressor or axis of rotation, that is denoted by B and beta 1. And this is relative velocity at exit, relative velocity at you know, inlet, and absolute velocity at inlet, and this is absolute velocity at exit. And VW is the component of the relative velocity, sorry, the component of the absolute velocity which causes whirl, and this is velocity of flow, and same is the case for this V1 also, ठीक है. So down there अगर आप थोड़ा सा देख लें यहाँ पे, so this is blade velocity VB for both is for both are the same. As I told you, velocity of flow is also equal, so you will see that a relative velocity an outlet triangle is less than that in the obviously because of friction, right. VR1 जो है ना वो VR से कम होगा because of friction. friction वहाँ पे होता है. अगर friction को आप ideally नलीफाई कर दें तो k will be equal to 1 and vr will be equal to vr1 anyways. So यहाँ पे work done having the same formula for compressor per kg of air directly यहाँ पे लिखा है चा, not in case of force but just this is what per kg means आपके पास this one is m dot जो है ना this is unity, right? So rate of change of momentum जो है ना that is your force. Rate of change of momentum क्या है? That is your force. M dot into velocity difference. तो m dot into this velocity difference. This will be your force and if you multiply the force with Vb that will be your work. ठीक है, पावर जिसको आप कह सकते हैं. समटाइम्स वर्क फैक्टर, अच्छा ये समटाइम्स जो है ना वर्क फैक्टर इसके साथ मल्टीप्लाई किया जाता है. व्हाट इज वर्क फैक्टर? अच्छा ये चीज इंपॉर्टेंट है, ये आपके बुक में भी शायद डिस्कस किया गया होगा. रिमेंबर वर्क फैक्टर इज बेसिकली in simple words it takes care of the losses over here or the assumptions over here. ठीक है, like what you know we have actually, बल्कि यहाँ पे चले आप देख लें, you know here let's say the air enters to this rotor, this compressor. So here this is the air, okay, that is impinging at the outer tip. ठीक है, air जो है ना यहाँ पे भी आपके पास आ सकता है. ठीक है, the air is impinging down there at the root, right? So this is actually the blade height. ठीक है, so we are considering that the air basically impinges at mid height. ठीक है, ठीक है, ऑब्वियसली डिफरेंट होगा ना, यहाँ पे जो है इसकी वेलोसिटी डिफरेंट होगी, मींस if you are considering the blade, okay, so the velocities will be different, but we are considering that the air actually impinges at what, at the mid height. ठीक है, तो इसलिए जो है ना this assumption is and there are also some other assumptions, okay, so we are considering that the airflow will be laminar, okay, although में थोड़ी बहुत टर्बुलेंस होती है. सो फॉर दैट रीजन जो आपके पास वर्क फैक्टर है ना इसको मल्टीप्लाई किया जाता है. ठीक है, कि टू टेक केयर ऑफ दीज assumptions we in order to find out the actual work done by the compressor on the air, ठीक है, you need to multiply this work factor. ठीक है, यानी एक्चुअली जो है ना आपके पास वर्क डन जो है वो कम होगा, लेकिन वर्क फैक्टर जो है ना इसको थोड़ा सा बढ़ाएगा कि वर्क डन जो है ना इसमें ज़्यादा वो हुआ है. ठीक है, तो दिस इज एक्चुअली द फार्मूला एंड देयर आर सम, दिस इज सम स्लाइड दैट इज कंपैरिजन ऑफ सेंट्रीफ्यूगल एंड एक्सियल फ्लो कंप्रेसर. सेल्फ एक्सप्लेनेटरी है, आप खुद से देख सकते हैं. बहरहाल द सेंट्रीफ्यूगल कंप्रेसर एंड दिस इज एक्सियल फ्लो कंप्रेसर. सो द फ्लो ऑफ एयर इज परपेंडिकुलर टू द एक्सिस ऑफ कंप्रेसर. रेडियल फ्लो इसको परपेंडिकुलर कहते हैं. ठीक है, यानी एक्सिस ऑफ कंप्रेसर जो है उसमें जो है दिस इज फॉर एग्जांपल एक्सिस ऑफ कंप्रेसर एंड दिस इज द रेडियल एंट्री. सो दिस एंगल इज 90. They are saying perpendicular. The flow of air is parallel to the axis of compressor. For that reason, this is known as axial flow compressor. ठीक है, it has low manufacturing and running cost comparatively to this one. यहाँ पे जो है ना इसका रनिंग और मैन्युफैक्चरिंग कास्ट जो है ज़्यादा है. एज आई टोल्ड यू द ब्लेड्स पर्टिकुलरली, ओके, दे आर हैविंग एरोफाइल क्रॉस सेक्शन, तो इसकी जो मैन्युफैक्चरिंग है एज कंपेयर टू द इम्पेलर ओवर हियर, दिस इज कास्टली. ठीक है, एंड इट रिक्वायर्स लो स्टार्टिंग टार्क, राइट? Just if you provide some pre-whirl, okay, so it will start and you know the impeller then rotates, okay, and it requires high starting torque, and it is not suitable for multi-staging. इसमें multi-staging आसानी से नहीं होती, इसमें staging जो है ना बहुत आसानी से होती है, as you saw over there. ठीक है, that we have rows and you know blades and stators stage, okay. So यहाँ पे मल्टी स्टेजिंग है. इट रिक्वायर्स लार्ज फ्रंटल एरिया. ऑब्वियसली फ्रंटल एरिया इसका ज़्यादा होता है, इसका फ्रंटल एरिया इतना ज़्यादा नहीं होता. ठीक है, और ये लेंथ में ज़्यादा होते हैं, दे आर लेंथी बट अ बिट कॉम्पैक्ट फॉर्म, राइट, एंड फॉर दैट रीजन दे आर यूज्ड इन द एयरक्राफ्ट. इसका फ्रंटल एरिया अगर ज़्यादा होता सो यू कैन नॉट यूज इट इन द एयरक्राफ्ट बिकॉज ऑफ हैविंग मोर एंड मोर ड्रैग force, okay, applied on the surface or the frontal area of the compressor. So for that reason they are used in the this one. Okay, this is actually application of compressor को अगर थोड़ा सा आप देख लें. So this yellow one is reciprocating compressor, and red one is centrifugal compressor, and this green one is axial compressors, right? So this is the design pressure, and this one is volume flow rate. So if you want, you know, to use it for very high pressures, but your requirement for the flow rate or the volume flow is not too much, you can use this reciprocating compressor. But if you want that at the same time we are having the more pressure, we want more pressure, but also a bit more volume flow, so you can use this centrifugal compressor. But if you want a relatively low pressure but too much volume flow, so you can use the axial flow compressor. And it is the case in the aircraft engines, okay, because over there we want to have more and more flow over there, because that flow is then, you know, exhausted, okay, or that flow is then exits through the nozzle, and the propulsion or the jet propulsion is प्रोड्यूस्ड ओवर देयर. ठीक है, सो ये चॉइस ऑफ कंप्रेसर है, किस जगह के ऊपर क्या आपने यूज़ करना है, राइट. देयर इज अनदर थिंग दैट इज रिलेटेड टू axial flow compressor. इसको हम कहते हैं degree of reaction. A simple thing, what degree of reaction is, it is an important term in the field of axial flow compressor only, which may be defined as the ratio of the pressure rise in the rotor blades to the pressure rise in the compressor in one stage. ठीक है, क्या मतलब है इसका, कि the pressure rise in the rotor blade में कितना pressure rise होता है, and pressure rise in a single stage. ठीक है, तो इन दोनों का जो रेशो होता है ना, इसको हम कहते हैं डिग्री ऑफ रिएक्शन. मोर इज द डिग्री ऑफ रिएक्शन, मोर विल बी द, यू नो, द प्रेशर प्रोड्यूस्ड ओवर हियर. ठीक है, तो यहाँ पे जो है ये कहता है कि एज अ मैटर ऑफ फैक्ट द डिग्री ऑफ रिएक्शन इज यूजुअली केप्ट एज 0.5 या 50%. ठीक है, इसका क्या मतलब है, 50% का मतलब ये है कि हाफ, लेट्स से फॉर एग्जांपल हाफ ऑफ द pressure, let's say for example, is increased in a stage is, let's say, 2 units, so half of it should be in the blades. ठीक है, यानी means half of it should be, you know, increased in the rotor blades. ठीक है, so the pressure rise in rotor blades will be half of what is there in the, you know, in the whole stage. ठीक है, तो इसको 0.5 रखा जाता है, मींस 50% रखा जाता है. ठीक है, अमूमन. अच्छा, अब 50% जब हम रखते हैं तो इसके लिए एक कंडीशन है कि हाउ प्रैक्टिकली इफ यू वांट दिस डिग्री ऑफ रिएक्शन शुड बी 50%, so what should be, you know, the configuration, and what should be, you know, the shape of the or the cross section or the shape of the, you know, this blades over there. ठीक है, तो उसकी तरफ हम जाते हैं. तो मैथमेटिकली डिग्री ऑफ रिएक्शन इज प्रेशर राइज इन रोटर ब्लेड्स, यही चीज है. अच्छा, इस बात जो है ना, कंप्रेशन, ये यू नीड टू मल्टीप्लाई the pressure rise per stage multiply convert it to pressure energy. ठीक है, so this is the pressure rise, mv square. Half mv square is the, you know, half mv square is a wait, let me check this connection. हालांकि ये कनेक्शन थोड़ा सा हो गया है. Okay, we are here. Right. Right. So this is what half mv square होता है हमारे पास, ठीक है. We have half mv square, the kinetic energy. So this is what kinetic energy at entry is half. M is taken as unity over here, so half VR1 square, right? And this will be half VR1, sorry, VR square, and this will be VR1 square. So this is change in kinetic energy, right, of the working fluid at entry and exit. And this energy or kinetic energy is imparted or it is converted to fluid, and the pressure will increase by this one, right? Similarly, we just discussed over here that pressure rise in a single stage, ठीक है, ये pressure rise है, ठीक है. That is what, that is the work done by the compressor on air, ठीक है, ये अभी हम डिस्कस किया. That is what, that is converted to pressure energy, ठीक है, per stage. अभी इससे पहले हमने डिस्कस किया for axial flow compressor, right? So if you just simplify this, this will be the combined velocity diagram with 50% degree of reaction, ठीक है. 50% degree of reaction के लिए अगर आप इसको करेंगे ना तो it will look like this, okay. And later on from this figure, okay, this is 29.9, I think, yes. From this figure they are saying that if you want to find out that इसी figures के साथ ही है, अच्छा. So first of all, let us draw a combined velocity diagram for an axial flow compressor with degree of reaction as a 0.5, right? So फर्दर जो है ना इसको थोड़ा सा इसी डायग्राम से डिस्कस किया गया है. वी आर नॉट गोइंग टू डिस्कस देम फर्दर बिकॉज दिस इज एक्चुअली थोड़ा सा इसमें जो है ना जस्ट मैथमेटिक्स इन्वॉल्व है, no engineering involved over here. So from the geometry of the figure we find that because we are interested in what, we are interested in basically in these things. We need to find out all these things, right? VR1, VB, VW1 and VW. We are interested in this thing. In order to put them over here, we can find out the degree of reaction for a particular compressor, ठीक है. तो बाद यहाँ पे जो आपके पास these calculations are purely to draw what, to find out what, to find out VW. अभी VW क्या है? VW from this particular figure is equal to this one, AB minus AE. This is your AB, right? This is AB minus AE. So this will actually give you VW. Now AE or AB क्या है? You can find out from this, this is actually this one, VB minus VF tangent beta, simple है. Similarly, you need to find out VW1. So put them over here. You will see that this is equal to the difference between velocities. And if you want to find out VR and VR1, okay, so देखने बल्कि I will suggest कि so now we have the difference between the relative absolute relative velocities, the relative velocities entry and exit and velocity of barrel over here, ठीक है. So you can just put them over here, okay, and you can find out this R is equal to this one. And then further they are saying that if what is R? R is basically degree of reaction. So let's say for example if your degree of reaction is 50%, so you need to put 0.5 over here, ठीक है. तो 0.5 जो है ना आप यहाँ पे put कर लें and further simplify कर लें. So you will be having VB, that is velocity of blade, and this velocity of flow, right? And from the geometry they are saying that we find that VB by VF जो है ना, VB by VF, ठीक है. किस geometry से? From that figure 29.9, you will see that VB by VF is equal to tangent alpha plus tangent alpha 1. So this means that let's say for example this is equation 1, right? You can put in place of VB by VF, you can put what? You can put tangent alpha plus tangent alpha 1, right? And at the right side this is actually over this thing. So tangent alpha plus tangent alpha 1 in place of VB by VF is equal to tangent beta plus tangent beta 1. And from here you can see that what, your beta, okay, this your beta is angle beta is equal to angle alpha 1 and your angle beta 1 is equal to angle alpha. ठीक है, so this means that बल्कि यहाँ पे लिखा भी है, it is thus obvious that for 50% degree of reaction the compressor will have symmetrical blades. So if you practically ensure that the blades of the compressor are symmetrical in configuration, so you can say that we can obtain the 50% degree of reaction where half of the pressure rise will be due to rotor blades and remaining half, the other one will be आपके पास जो है वो स्टेटर से होगा. सो टोटल जो है वो 2 होगा. मींस हाफ ऑफ the pressure is raised, okay, or increased by rotor blades and half will be increased by the stator blades. ठीक है, तो ये जो है ना टोटली पर स्टेज आपके पास जो 2 यूनिट्स इंक्रीज होगा. दिस इज एक्चुअली नोन एज अ डिग्री ऑफ रिएक्शन. ठीक है, ये एक्सियल फ्लो कंप्रेसर के साथ है, ये आप कर सकते हैं. इसके ऊपर एक एग्जांपल है, आप इसको आसानी से कर सकते हैं. दिस इज बेस्ड ऑन द सेम ट्राइंगल. Just ये आपको look at this, an axial flow compressor with a compression ratio is 5 draws air at 20 degree C and delivers it at 50 degree C. ये सारे आपको given है, T1 and T2 etc. ठीक है, compression ratio P2 by P1 भी given है. Assuming 50% degree of reaction, R is VF आपने फाइंड करना है, ब्लेड वेलोसिटी VB is 100 मीटर पर सेकंड. आल्सो फाइंड द नंबर ऑफ स्टेजेस, दिस इज इंपॉर्टेंट. ठीक है, आल्सो फाइंड द नंबर ऑफ स्टेजेस in order to increase pressure from 1 unit to 5 unit. ठीक है, how many stages should be there in the axial flow compressor. ठीक है, तो वो आपने फाइंड आउट करना है. टेक वर्क फैक्टर इज इक्वल टू दिस वन, अल्फा बीटा CP एटसेट्रा, ये सारे आपको गिवन है. ठीक है, तो बहरहाल इसको आप वर्कआउट करें. देयर इज नो डिफिकल्ट थिंग ओवर देयर, बट जस्ट यू नीड टू लुक एट दिस. दिस विल बी द टोटल वर्क रिक्वायर्ड. इसने फाइंड आउट किया है टोटल वर्क रिक्वायर्ड, वो ही है. अच्छा, दिस वन, वेयर इज दैट, दिस इज ये पर स्टेज है. टोटल वर्क शायद किस जगह के ऊपर इन्होंने, हाँ, दिस इज द टोटल वर्क. सो टोटल वर्क रिक्वायर्ड, ठीक है, in order to get or in order to increase the pressure from 1 to 5 units, 5 bar. ठीक है, and then per stage भी जो है ना इन्होंने find out किया है. So this is actually per stage, that is 5.55 kg per kilogram, right? So very simply, if you want to find out number of stages, then you need to have total work required divided by work done per stage. So इससे जो है ना 5.4 आता है. तो इस तरह you need to round this and you can say that if you have 6 stages of the axial flow compressor, you can get this pressure ratio. ठीक है, so if you increase this number of stages, this will also increase. ठीक है, and if you decrease it, this will also decrease. So for that particular pressure ratio, you can have this 6 stages of the axial flow compressor, right? So this is actually the end of this particular lecture, and you need to, as far as the problems are concerned, particularly for chapter 11, so you need to practice those problems for which we actually discuss the topics. ठीक है, so the topics that we discussed in chapter 11 and the example that they are related to those topics are the problems related to those topics. You need to cover them for the final term exam, right? Thank you very much.